The basic principle behind IC engines is surprisingly simple: controlled explosions. These explosions are meticulously timed and manage to ensure that the engine runs smoothly and efficiently. That's right, we're essentially harnessing miniature explosions to generate power. These explosions occur in rapid succession, creating a continuous source of energy that propels the vehicle forward. We take a flammable substance like gasoline or diesel, mix it with air, compress it tightly, and then ignite it with a spark. This mixture is crucial because the right balance of fuel and air ensures optimal combustion and power output. Boom! That explosion forces a piston to move, and this linear motion is converted into rotational force that turns the wheels of your car. The piston's movement is a key component in transforming the energy from the explosion into usable mechanical energy. Imagine a syringe for a moment. You pull back the plunger, sucking in air. That's similar to the intake stroke in an engine. During this stroke, the intake valve opens, allowing the air-fuel mixture to enter the cylinder. Now cover the opening and push the plunger. You're compressing the air, just like the compression stroke. In this phase, the intake valve closes, and the piston moves up, compressing the air-fuel mixture to prepare it for ignition. Finally, imagine a tiny explosion inside the syringe, forcing the plunger back out with great force. That's the power stroke. This is where the magic happens, as the spark plug ignites the compressed mixture, causing a powerful explosion that drives the piston down. This controlled combustion is the heart of an IC engine's operation. Without it, the engine wouldn't be able to produce the necessary power to move the vehicle. The continuous cycle of intake, compression, explosion, and exhaust creates the mechanical energy that drives our vehicles and countless other machines. Each of these strokes plays a vital role in ensuring the engine runs efficiently and effectively. It's a symphony of controlled chaos, a testament to human ingenuity. The precise timing and coordination of these strokes are what make internal combustion engines so powerful and reliable. But hold on, there's more than one way to skin a cat, or in this case, design an engine. Engineers have developed various types of engines to meet different needs and applications. Let's explore the two main types: two-stroke and four-stroke engines. Two-stroke engines are simpler and lighter, making them ideal for smaller applications like motorcycles and chainsaws. Four-stroke engines, on the other hand, are more efficient and durable, making them the preferred choice for cars and larger machinery. Each type has its own unique advantages and disadvantages, and understanding these differences can help you appreciate the engineering marvels that power our world. Now, just like there are different types of cars for different drivers, there are different types of internal combustion engines for different purposes. Each engine is designed with a specific function in mind, catering to the diverse needs of various machines and vehicles. The two most common types are two-stroke and four-stroke engines. These engines are the backbone of many machines we use daily, from small handheld tools to large vehicles. Both operate on the same basic principle of combustion, where fuel is ignited to produce power. However, they go about it in different ways, each with its own unique cycle and characteristics. Imagine a two-step dance versus a four-step waltz. The two-stroke engine is like the quick, energetic dance, while the four-stroke engine is more like the elegant, methodical waltz. The two-stroke engine is like the quick, energetic dance, completing a power cycle in just two strokes of the piston. This means it fires once every revolution of the crankshaft, making it a powerhouse in a compact form. It's simpler, lighter, and packs a punch for its size. The design is straightforward, with fewer moving parts, which makes it easier to maintain and repair. That's why you'll often find them in smaller machines like chainsaws, lawnmowers, and some motorcycles. These applications benefit from the high power-to-weight ratio and the simplicity of the two-stroke engine. The four-stroke engine, on the other hand, is like the elegant waltz, completing a power cycle in four strokes of the piston. This means it fires once every two revolutions of the crankshaft, resulting in a smoother and more controlled power delivery. It's more refined, efficient, and produces fewer emissions. The four-stroke engine's design allows for better fuel efficiency and cleaner combustion, making it more environmentally friendly. This is the engine you'll find in most cars, trucks, and larger machinery. Its efficiency and reliability make it the preferred choice for vehicles that require consistent and long-lasting performance. So, why choose one over the other? The decision often depends on the specific needs of the application and the desired balance between power, efficiency, and simplicity. It all boils down to the specific application. For instance, in handheld tools where weight and power are critical, the two-stroke engine is ideal. In contrast, for vehicles where efficiency and emissions are more important, the four-stroke engine is the better choice. Two-stroke engines are great for power-to-weight ratio and simplicity. They are easy to start, quick to accelerate, and can operate in any orientation, making them versatile for various small machines. While four-stroke engines excel in efficiency, emissions, and overall performance, they provide in stable operation, which is crucial for the comfort and reliability of passenger vehicles. Let's learn about the parts of IC engines. Cylinder, the core chamber where combustion happens. Piston, moves up and down inside the cylinder, transferring combustion energy to the crankshaft. Crankshaft, converts the piston's up and down motion into rotational power. Connecting rod, connects the piston to the crankshaft, transferring motion. Camshaft, controls the opening and closing of intake and exhaust valves. Valves, intake and exhaust, allow air and fuel in and let exhaust gases out. Spark plug, ignites the air-fuel mixture in gasoline engines. Fuel injector, injects fuel directly into the combustion chamber. Piston rings, seal the gap between the piston and cylinder wall, preventing gas leakage. Cylinder head, seals the cylinder and holds valves and spark plugs. Flywheel, helps maintain smooth engine operation by storing rotational energy. Oil pump, circulates oil to lubricate engine parts. Cooling system, water pump, regulates engine temperature. Chain belt, keeps the camshaft and crankshaft synchronized. Timing chain, belt, keeps the camshaft and crankshaft synchronized. Exhaust manifold, channels exhaust gases out of the engine. Intake manifold, distributes air-fuel mixture to the cylinders. Turbocharger, if applicable, boosts engine power by increasing air intake. Alternator, charges the battery and powers electrical systems. Starter motor, starts the engine by turning the crankshaft initially. Gaskets, seal engine parts to prevent leaks. Oil pan, holds engine oil for lubrication. Each component, no matter how small, plays a vital role in this intricate dance. From the pistons to the valves, every part must work in perfect unison to ensure the engine runs smoothly and efficiently. That's the four-stroke engine in action. The up and down motion of the piston is what drives the engine, converting fuel into the power needed to move the vehicle. It all starts with the intake stroke. This is the first step in the four-stroke cycle, where the engine begins to draw in the air-fuel mixture that will eventually be ignited to produce power. As the piston moves down, it creates a vacuum that sucks in a mixture of fuel and air through the intake valve. This mixture is crucial because it contains the energy that will be released during the combustion process. The engine needs this air-fuel mixture to generate power. Next comes compression. The intake valve closes and the piston moves back up, squeezing the fuel-air mixture into a tight space. This compression is essential because it increases the mixture's potential energy, making the subsequent explosion much more powerful. This compression is crucial because it makes the subsequent explosion much more powerful. The more compressed the mixture, the more forceful the explosion, and the more power is generated to drive the piston down. Now the power stroke. This is where the magic happens, transforming the potential energy stored in the compressed mixture into kinetic energy. With the fuel-air mixture highly compressed, a spark plug ignites it, creating a powerful explosion that forces the piston back down with great force. This explosion is the heart of the engine's power, the moment where chemical energy is transformed into mechanical force. This is the heart of the engine's power, the moment where chemical energy is transformed into mechanical force. The force generated by this explosion is what ultimately drives the vehicle, propelling it forward. Finally, we have the exhaust stroke. This is the last step in the four-stroke cycle where the engine expels the burnt gases produced during combustion. As the piston moves back up, it pushes out the burnt gases through the exhaust valve, clearing the cylinder for the next cycle to begin. This step is crucial for maintaining the engine's efficiency and preventing the buildup of harmful gases. Just as our bodies need to get rid of carbon dioxide, the engine needs to expel these burnt gases to continue functioning properly. And so, the cycle repeats itself, thousands of times per minute, creating the power that drives our vehicles and countless other machines. This continuous cycle of intake, compression, power, and exhaust is what keeps the engine running smoothly and efficiently. The design of the four-stroke engine is a marvel of human ingenuity.